All right, let's talk about the conic section of the ellipse. By definition, ellipse is a set of all points x, y in a plane, the sum of whose distances from two distinct points, known as the foci, is a constant. So, any point on this red ellipse, foci to point, point to foci, add the two blue lines together, you get a constant sum. The green lines, those distances added together, is going to be the same as the sum of the blues. These two black lines, same thing. They both add up to the same value. So these foci are located at negative C0, C0. So the distance from the center to a foci will be represented by the variable C. Again, this point P can be anywhere on the curve. Now, to find this sum, we need to define these other points. So from the center to the vertices, all right, that's negative A0, A0. A is going to be the biggest value here. Then these are called covertices. A lot of authors aren't going to identify them as covertices, but I will. There's still a turning point on the curve. 0B, 0, negative B. So center to this point is B, center to the vertex A. Now, this distance, this constant sum that we're looking for, if you were to take point P and I were to place it right here on this vertex, I would have to go from this foci through the center, through this foci to that vertex. That covers everything right there. Then I come back to this foci, which I've already covered that distance. I come back. That's like taking that short distance and putting it over here. So this constant sum is 2a. If this was to be our point P here, then foci to this point creates this distance A, this distance is A. So now, with this right triangle here, what's going to happen is this creates a different representation of the Pythagorean theorem. B squared plus C squared equals A squared. Well, I prefer to have the A squared and the B squared together, so what I usually do is I'm going to need the Pythagorean theorem with a minus sign. Now, when we talk about the equation of the ellipse in standard form, x squared over a squared plus y squared over b squared, a squared will always be the bigger of the two denominators because a is going to be greater than or equal to b, and a and b have to be greater than 0, which just means they've got to be positive because we have to go to a positive distance from when we count. All right? Now, if a is underneath the x squared, you have what we call more of a horizontal. It stretches more along the x-axis than it does the y-axis. If we have a vertical ellipse, it's stretched more along the y-axis. And now your b squared is underneath the x squared. That's the shortest distance. And the a squared is underneath the y squared. Now we're counting more up and down. So these are all centered at the origin. If we move our center to h comma k, like we did with our parabola, we could change the vertex to h comma k. The changes in the equation that you will see is the minus h and the minus k will be with the x and the y. And we just relocate our center and we count left and right A, up and down B, or up and down A, left and right B for our ellipse. So again, the major axis is the line segment joining the vertices. That distance is 2a. That's the major axis. The minor axis connects these two covertices. That distance is 2b. Remember, the constant sum and the length of the major axis are the same value, 2a. And if A and B, whoops, come back here, I wasn't done with you yet. If A and B are exactly the same, then the ellipse is a circle with a radius of A. So this would be A squared, this would be A squared. This is equal to 1. You can multiply both sides by an A squared, and that would be your R squared from a circle. All right, so let's look at graphing one. So we're going to find the center. Notice nothing's being added or subtracted to the x and y, so we're at the origin for our center. So we plot that point. Now we're going to find A, B, and C. So A is coming from the biggest denominator, 36. That's my A squared. Take the square root of 36 is 6. It's underneath the x squared. You count left and right, 6 squares. So on my center, the x coordinate, I add and subtract 6 to that 0, which makes it a positive -6, 0. So to the left 6, to the right 6, label those as capital V. Underneath the y, there's my smaller value, that's my b squared. B is equal to 3. Once I take the square root, we're going to count up and down 3. There's my points. Again, like I said, if you want to put right underneath the vertices, co-vertices, they would be 0, plus or minus 3. I will probably ask you for it, but in the homework, like I said, a lot of these authors don't acknowledge the co-vertices. I've seen in some particular books where they're called the major vertices because they're the endpoints of the major axis, and then they call the co-vertices, they call them the minor vertices, which are the endpoints of the minor axis. But they should get a name. They're entitled to some recognition here. So we're going to make our graph. We make our best oval around those 4 points. Our foci is the Pythagorean theorem with the minus sign. A squared minus b squared equals c squared. So 36 minus the 9, a squared minus b squared. Take the square root of that. So that's going to be the square root of 27, which will be just approximately 5 point something. I could reduce that or simplify it to 3 square root of 3. So those foci will change the x-coordinate just like in the vertices, so positive, negative, 3 radical 3, 0. And if I plot those are going to be just a little bit past the 5. There's my foci. We could take the square root of 27 in the calculator and find a good decimal representation. All right, next, something that you'll need for the test is completing the square. This is in general form. We need to put it in standard form. So we need to group the x's together. We need to group the y's together. And we're going to subtract this 10 over to the other side and put in 2 plus blanks. Now, in order to complete the square, notice what I did with the y terms. I have to have a 1 in front of my y squared. So I took out the 3 as the GCF from both of my y terms. So 3 times y squared minus 4y plus blank. Well, this blank is going to get multiplied by 3, so you'll notice over on the right side, I put 3 times the parentheses around the blank that represents the y. This blank represents the x. So if I complete the square, we'll take half of positive 2, which is positive 1. We square that, that's a 1. Half of negative 4 is negative 2. We square that, that's a 4. So we're going to get negative 10, looks like plus 13. So that will equal 3 on the right side. And you will have x plus 1 squared x plus 1 squared plus 3 times y minus 2 squared equals 3. Divide everything by 3 because the ellipse needs to have this equal to 1. 3's cancel, so there's my equation in standard form. So my center, find the x, change the sign, negative 1, find the y, change the sign, positive 2, plot that point. We'll go ahead and find a, b, and c, so 3 is the bigger value. It's underneath the x, so we're going to count left and right, the square root of 3, which is approximately 1.7-ish. So negative 1 plus or minus the square root of 3, 2, that's going to be the location of my points. So a lot of times they're going to want this as an exact value, so don't change these to decimals. change them to decimals just to get a good approximation. Like I said, it's close to 1.7 to the left, 1.7 to the right. 1 is my b squared. The square root of 1 is 1. Now it's underneath the y, so we count up and down 1. So up 1, down 1, those are my covertices. And then I draw in my ellipse. Foci, Pythagorean theorem with the minus sign. 3 is the a squared. 1 is the b squared. I subtract those two. That's 2. The square root of 2 is the square root of 2, or approximately 1.4. So again, positive, negative, square root of 2, added and subtracted to the negative 1. So negative 1 plus or minus the square root of 2 comma 2 is the location of my foci. Approximately 1.4 to the left, 1.4 to the right. We're really close with our vertices and foci. So again, make sure you're ready for completing the square on the test. Example 3, find the equation of the ellipse from the given graph. Okay, so what we need to do here, it's more horizontally stretched. So the x minus h binomial squared has to be over the a squared. So what I need to do is find the center, count how far I counted left and right from the center, how far I count up and down from the center. So we'll cut this in half horizontally, then in vertically. So we are at 2, 1 for the center. So if you want, put 2 and 1 in for h and k. To the left, 3. To the right, 3. So a is 3. Up 2, down 2. B is 2. So a is 3, b is 2. Plug those in. 3 squared is 9. 2 squared is 4. There's the equation. My foci, Pythagorean theorem with the minus sign. A squared 9 minus b squared 4 is 5, the square root of 5. So we'll add and subtract the square root of 5 left and right, because that's the directions of my vertices. So 2 plus or minus the square root of 5, comma 1. Example 4, find an equation of the conic section that satisfies the given conditions. We have an ellipse with vertices at 0, 8, 0, negative 8. So I'm going to have my squares count by 2. So there's 0, 8, there's 0, negative 8. Well, right in between has to be the center. So we're centered at 0, 0. And the distance from the center to the vertex is 8. So that's my a value. Foci, 0, comma, plus or minus 4. So again, my squares are counted by 2. So there's 0, 4, 0, negative 4. So that distance from the center to the foci, that's c. So c is equal to 4. So now my equation is x squared over b squared, because I'm stretching more up and down, and my a squared will be underneath the y squared. So we can put the a in here, so that's going to be y squared over 64. Now we have to find b squared, so to the Pythagorean theorem we go. We can say c squared is equal to, c squared, 4 squared, 16, is equal to 64 minus b squared. Add over the b squared, subtract over the c squared. You can do it as a formula, or you can plug in the numbers. Either way, you get 64 minus 16 is 48. Put that 48 underneath your x squared. There's my equation. Example 5. Let's find the equation of our ellipse with a major axis of 6 and the foci at 0, 0, and 4, 0. So again, I'm going to make a rough graph. Foci, 0, 0, 4, 0. In between my foci has to be my center. That's 2, 0. And therefore my c is going to be a distance of 2. Now they didn't give me the vertices, so how do I find the a? Remember, the major axis is 2a. And if the major axis is equal to a length of 6, then 2a equals 6. Divide over the 2, a is equal to 3. If you want to count 3 squares to the right and 3 squares to the left and plot the vertices, you're more than welcome. But I can see that this is being stretched more horizontally. So this is going to be x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. Put 2 in for h, 0 in for k, and we'll put 3 in for a to make this a 9. Now, we don't need to have y minus 0. We can just write that as y squared. We need to find b squared. So to the Pythagorean theorem we go. C squared equals a squared minus b squared. Add the b squared to the left, subtract the c squared to the right. There's my Pythagorean theorem right now with b squared by itself. So plug in the a. That was 9. C was a distance, we said, of 2. So 9 minus 4 is 5. Take the square root of 5. Oh, check that. We don't need to take the square root of 5 because we just had to find b squared. We'll just put that underneath our y squared. I'm thinking we had to find the points for our foci. Example 6, find the equation of our conic section, the ellipse again. Make a graph. We're going to have plus or minus 4 comma 0. So because I see plus or minus 4, I know I'm counting left and right with my foci, so my a squared is underneath my x squared. And it passes through the point negative 4 comma 1.8. So I make my graph. Negative 4, 0, 4, 0. Again, center is at 0, 0. Kind of dead giveaway with the plus or minus comma 0. And we have the check that, c value will be a distance of 4. That's my c value. We're going to plot this other point at negative 4 and 1.8, right about there. Well, wait a minute, you didn't give me the vertices. Well, they did, we just have to take a little time to find it. So if you connect foci 1 to P, and then P back to foci 2, this is your two distance that have to add up to be 2a. So if I can find those distances, add them together, that will be my 2a. Well, let's see. From P to F1, we just went up 1.8. P to F2, I have to do the distance formula. So the distance from this P to this F2, negative 4 minus 4, or 4 minus negative 4. Either way, it's going to be 8. And the 1.8 minus 0 is 1.8. So that's this distance squared. So this is my y2 minus y1 squared. This is my x sub 2 minus y sub 1 squared. So crunch out the numbers here. This comes out to be 8.2 after you take the square root of these two numbers, added together and squared. 1.8 plus 8.2 is 10. 10 divided by 2 is 5. So A is the distance of 5. So we can put 5 in for the A squared, then use our Pythagorean theorem to go find B squared again. C squared equals A squared minus B squared. Add over the B squared, subtract over the C squared. Put in 25 for the A squared. We'll put 16 because C is 4. 16 for C squared, subtract the 2, B squared is 9. Put that underneath the Y squared. There's the equation. Now, another way that you could have found the distance from P to F2, you could have done the Pythagorean theorem. This distance is 1.8. This distance from foci to foci is 8. 1.8 squared plus 8 squared. Add those two together. That would give you c squared up here, if you will, in a traditional Pythagorean theorem, the hypotenuse squared. Then take the square root of that, then take this number plus your 1.8, and you'll still come up with 10. Okay, example 7. We're going to find an equation for our conic that satisfies the given conditions. Again, we're looking at an ellipse. The center is at negative 1, 4, vertex at negative 1, 0, foci at negative 1, 6. So let's build our xy coordinate plane. We'll plot our center at negative 1, 4. We'll plot our vertex at negative 1, 0. All right, that tells us right now the distance for A, our A value will be 4. Plot your foci at negative 1, 6. That tells me my distance for C is 2. And based on the changes here of these points, we have a vertical ellipse. If you want to plug in the other points, you can, but I think you can still see that we have a vertical ellipse. So we're going to need the a squared underneath our y minus k squared. And we can start plugging in our values. You have your h or k. We have an a, so we can put 16 underneath our y minus k squared. So again, we're going to go grab our Pythagorean theorem with the minus sign, plug in the a squared, 16, plug in c squared, which will be 4. You could solve for b squared or solve for b squared as a formula first, then plug in your numbers. 16 minus 4 is 12. Put that in for b squared, and there is the equation of our ellipse. Now, we have this thing called eccentricity. It is given by E sub cc. That's just the first 3 letters. It is equal to c over a. Well, since a is the largest value in the ellipse, this fraction is always going to be less than 1. So if your fraction is really close to 0, that means you have a small c value with a large a value, we're closer to 0, then the foci is close to the center and looks more like a circle. And in reverse, if we have a really large c value, really close to a, that means, okay, now my fraction is getting really close to 1. Then the foci are going to be closer to the vertices. And it's going to be more of an elongated ellipse. All right, and that wraps up our ellipses.